Good morning, everyone. So today we will discuss thermodynamics. This part of this course, it includes two chapters. Chapter 20, which discusses the heat and the first law of thermodynamics. And then chapter 22, as in the book, which discusses the heat engine, entropy, and the second law of thermodynamics. So today we will start with chapter 20, where we're going to discuss the heat and the first law of thermodynamics. So thermodynamics is the study of energy transformation for a given system, including the heat, mechanical work, and basically how these energy transformations they're related to the properties of matter. So we're going to see this into details, but before to start, let's define a few basic concepts. So the first concept that we're going to define is a thermodynamic system. So what is a thermodynamic system? It's actually any collection of objects that is convenient to regard as one unit and that may exchange the energy with its surrounding. Like, for example, an air conditioner, refrigerant in the air conditioner. This can be seen as a thermodynamic system which can exchange the energy with the surrounding. And a side note, we describe the state of a given system using variables which we call the state variables, such as the pressure, the temperature, the volume, these kind of variables. So this is the first ingredient that we need to discuss or need to define. And then if we have a system, then a system can undergo some thermodynamic processes. So what do we call a thermodynamic process? Is a process in which there are changes in the state of a thermodynamic system, as we said earlier, defined by few variables, which we call state variables. So whenever this system undergoes some process during which there is variation in these variables, that we can call this process a thermodynamic process. Okay, now the energy relations in any thermodynamic process, they are related or described in terms of basically two quantities we are going to discuss in this course. So the way the system will exchange the energy with the surrounding, it's gonna be through two channels basically. First of all, through the quantity of heat added to the system, which we call Q. So the heat is defined as the transfer of energy across the boundary of a system due to a temperature difference between the system and its surrounding. So if we have this case and we have the heat exchange between the system and the surrounding, then this is the first variable which we will consider in this energy relations or energy transformation. And the second channel would be through the work done by the system. So if the system is doing some work, then this would be described by the work W. Now note that both W and Q, they could be positive or negative. I mean, for the work, this kind of clear because we have already seen this previously. But what does it mean to have a negative heat or positive heat? So we have to keep these notations in mind. The heat and the quantity of heat added to the system could be positive or negative in the sense that if the heat flow, it enters to the system, if the heat flow into the system, our heat is added to the system, then in this case Q is positive, and we are in this situation in here, the first situation, where you have, this is your system, and you have some heat which is added to the system through the red arrow. So in this case, we say that Q is positive. While if the heat flow out of the system, so that in this case, you have, this is your system, and the system is losing, he is providing heat to the surrounding, then in this case, we say that Q is negative. And, or in other words, negative heat means that the heat is flowing out of the system, and positive value of the heat means that the heat is flowing into the system. فإذا لما يكون الكيو positive يعني السيستم عم يربح heat، أما لما يكون الكيو negative السيستم يكون عم يخسر heat. And so this is what concerns the heat variable. And what concerns the work, also in the same way we can define the positive and the negative value of the work. هون نحن we defined the work previously هون in this line as the work done by the system هون بهيدي اللاين. So this is why we're going to define in the following way. If W is positive, that means that the work is done by the system against its surrounding, and that means that the energy is leaving the system. مع انه اذا كان ال W positive يعني السيستم هو اللي عم يعمل work على ال external surrounding، وبالتالي that means انه هو عم يخسر الانرجي من خزان الانرجي اللي عنده، لانه لحتى يقدر يعمل الورك عم يخسر انرجي. Like for example a gas expanding، اذا الغاز عم يعمل expansion وعم يدفش البستون لبرا، ف the fact انه هو عم يدفش البستون لبرا عم يعمل work على الاكسترنال surrounding، بالمقابل هو عم يخسر من هالانرجي يلي له لحتى يقدر يدفش البستون. اما the other case هو لما يكون W is negative. So in this case we say that the work is not done by the system but it is done on the system by its surrounding, and that means that the energy is entering in this case the system. وهذا الشيء نقدر نشوفه بهيدي الرسمه كمان، انه بهالحاله لما يكون السيستم عم يعمل work نقول انه W is positive but that means that the energy is leaving the system لانه هو اللي عم يعطي من الانرجي اللي عنده لا يعمل work على الخارج. اما بحاله W is negative that means that the work is done on the system، يعني العالم الخارجي هو اللي عم يعمل عليه work وبالتالي هو عم يربح energy. So these notations we have to keep them in mind. The when W is positive or negative, and what is the interpretation of positive or negative values of the work, and in the same way we have to keep in mind what does it mean to have a negative or positive Q, which is the heat. So we will continue with a second section where we are going to derive or to calculate the work done by a system during volume change. So let's consider that we have a given system, so it could be a gas or a liquid, inside a cylinder of cross-sectional area A. So let's say that this is our cylinder. This is the cross-sectional area. It's the surface of this area. هي ال A cross-sectional area. And with a movable piston, so in such a way that إذا كانت تمدد, for example, this gas inside the cylinder, it could push the piston لبرا، بتطلعه لبرا. Okay, and let the pressure exerted by the system at the piston to be P. So P is the pressure exerted by this thermodynamic system اللي هو من جوا on the piston. If P is the pressure exerted by the thermodynamic system on the piston and A is the cross-sectional area, then we can say that there is a force exerted on this piston with F equals to P times A. And that if we go back to the definition of the pressure, the kind of pressure we define it as the force per unit of area, and so F is equal to P times A. That sounds great. Now, if we know what is the force exerted on the piston, and we know how much is the displacement of the piston due to this force, then we can calculate the work done by the force F. So let's assume that the piston has moved through an infinitesimal displacement dx, okay, under the action of the force F. Then in this case, we can determine the infinitesimal work as given by, so إذا كان under the force F عم بيصير في displacement dx, then we can say that the infinitesimal work dW that is equal to F, so it's F dot dx, which is the scalar product between the force and the displacement vectors. But since here they are both in the same direction, so this is nothing else than F multiplied by dx. Now, if you just replace F by P times A, then you end up with P times A times dx. And since A times dx, this is nothing else than V, so you end up with P dV, where dV is the infinitesimal change in the volume. So this is the infinitesimal change in the volume. Now, if you have a finite change in the volume, يعني بدل ما نكون عم نطلع على dW عم نطلع على W, then W could be defined as the integral between the P dV between the volume V1 and the volume V2. So if the system undergoes a volume change between V initial denoted as V1 and V final denoted as V2, then the work done during this volume change is given by this expression, and this you should know and memorize because we may need to use it. So this is the work done by the system for a given volume change and a given volume change. Okay, now let's discuss two cases basically for this work. The general case is when the pressure can vary as a function of the volume. يعني ممكن يكون بالgeneral case هو بهالشكل التالي. This is the pressure as a function of V, and we could have the pressure varying as a function of V. So بهالحالة the work W مع إنه هو عبارة عن integral of P dV between V1 and V2, that means we are looking at this figure من ال V1 إلى ال V2. شو هو الwork؟ هو عبارة عن الانتجرال of P dV between V1 and V2, which is nothing else than the area under the curve in the PV diagram. هذا بنسميه PV diagram أو P as a function of V between the 2 points, point 1 and point 2, because we are looking at the volume change during this period, and so this time interval. وهذا شيء شو بيعني؟ يعني ها هي الاريا under the curve in this PV diagram. So this is the work. هيدا هو بهالحالة بتكون the work done by the gas, by the system on the external surrounding. So that is the general case. لما يكون في عنا P that could vary as a function of the volume. Now, if P does not vary as a function of the volume, يعني بهالحالة P remains constant while the volume changes or the volume volume variation occurs, then in this case, if P is constant, then we could write down W is integral of P dV between V1 and V2, and since P is constant, it get out of the integral between V1 and V2 of dV. والintegral of dV هي بكل بساطة V evaluated between V1 and V2, we end up with V2 minus V1 times P. So if that P, the pressure, is constant, then the work done by the system during a volume change is given by P multiplied by V2 minus V1. Another case is the case of an isothermal expansion of an ideal gas. So this is one of the particular cases which we may have or see in different applications. What do we mean by isothermal expansion of an ideal gas? You know what is an expansion of an ideal gas? And isothermal means that T, the temperature of the gas, remains constant during the expansion, so during this volume change. So let's actually calculate the work done by the gas in this case. So again, we start from the basic thing اللي هي إنه W is equal to the integral between V1 and V2 of P dV, right? But in this case, we are dealing with an ideal gas, and we know that an ideal from ideal gas law that PV is equal to nRT. So we can write down P as a function of the volume as P equals to nRT divided by the volume V. And so let's substitute the pressure by its expression inside the integral. So we end up with the integral from V1 to V2 of nRT over V times dV. Now, since N, R, and T, they are constant, N is constant, R is constant, and T is constant in this case because we are dealing with an isothermal expansion. يعني temperature عم بتضلها مثل ما هي. So nRT بيطلعوا لبرا, and so we end up with the integral between V1 and V2 or of dV over V. And so the integral of dV over V is nothing else than the ln. So we end up with nRT times ln V between V1 and V2. And so we end up with W equals W equals nRT multiplied by ln V2 minus ln V1. And if you just have a look at the properties of the ln function, you end up with this as nRT with ln V2 over V1 here ln V2 minus V1. So this can be written as ln V2 over V1. So this would be the work done by an ideal gas during an isothermal expansion. Given that هون بهالحالة we wrote down the work as a function of the volumes. Now, we can also write down this as a function of the pressure. So as a function of the pressure, we know that since we have an expansion at constant temperature, معناتها بنقدر نكتب P1 V1 equals ل P2 V2 لأنه من ideal gas equation أو law PV equals to nRT. بما أنه هون بهالحالة T is constant, so we know that PV is equal to nRT. بما أنه T constant يعني هي كلها صارت constant. وبالتالي if you look at the product between the pressure and the volume at any time it's not varying, it's not changing. That means between the initial configuration and the second configuration 1 and 2, this product is the same. And so if you divide V2 over V1 from this, we can deduce that P1 over P2 is equal to V2 over V1. So from here, we can actually write down W, the work done by the gas on the external surrounding as W equals N times RT multiplied by ln. Instead of V2 over V1, we're going to replace it with P1 over P2. So whenever you are asked about the work done by an ideal gas during an isothermal expansion, you can directly use one of these two relations depending if you have V1 and V2 or P1 and P2. And so let's just check, meanwhile, let's check the case of an expansion or the case of a compression. So let's take it number one, the case of expansion, according to what we have. So in the case of an expansion, لما يكون في عنا expansion معناتها إنه V2 is greater than V1, right? Which means that the ratio V2 over V1 is greater than 1. Okay, so if V2 over V1 is greater than 1, that means that ln V2 over V1 is positive, which means that the work W also is positive. And that is true. This is logic according to what we have said earlier, because if the gas is making an expansion, that means that it is exerting the work on the external surrounding, and therefore it's losing energy. So that means that the energy in this case is leaving the system. So let's study the case of a compression. So for the case of a compression, we should get the opposite. We should get W negative of A, but let's check that. For the case of a compression, in this case, V2, which is the final state, it's smaller than V1. So we expect that V2 over V1 is smaller than 1. And that means that the ln of the ratio V2 over V1 is expected to be negative. And that means W is negative. And again, this is something that is expected because in this case, that means that the energy is entering the system. Because this is the work done on the system by the surrounding. معناتها انه في energy عم تدخل على السيستم مش عم تطلع منه للسيستم. Okay, so that was an example of how to calculate the work in a given case اللي هو بهالحالة isothermal expansion of an ideal gas. So the thermodynamic process هو isothermal expansion. The thermodynamic system هو ideal gas. And we were requested to calculate the work done by the gas during an isothermal expansion. So we have used the definition of the W as we have derived earlier, given by W equals the integral of PdV between V1 and V2. So in this section, we're going to discuss the first law of thermodynamics. But to do so, we need first to define and to introduce what we call the internal energy of a system. So as you know, a system, when we say system, we mean matter, whether it's a gas or a liquid or any kind of thermodynamic system, we are dealing with matter. And the matter consists of atoms and molecules, which are made of more tiny particles and more elementary particles. So an internal energy is defined as the energy of a system that is associated with its microscopic components, which we call the atoms and molecules. So the internal energy includes kinetic energy of random, translational, rotational, and vibrational motion of molecules. It also includes potential energy within molecules and potential energy between molecules. So this is why here we have written down the internal energy of a system as the summation between kinetic energy related to any kind of random motion of the molecules inside the system, plus the potential energy of the molecules also inside the system, whether the potential energy within the molecules or between the molecules. So to understand how the system is exchanging energy with the surrounding, let's consider a system that is experiencing a change in its state. That means that the internal energy of the system, it goes from some U initial to U final. Under some energy transformation, the internal energy changes from U initial to U final in such a way that you have the variation in the internal energy given by delta U equals U final minus U initial. So the question is how the variation in the internal energy of the system given by delta U here is related to these energy transformations, to what happened in the system. So for this reason, let's define two things. Let's suppose that the system, it has absorbed a quantity of heat, which we denote by the quantity Q. And let's assume that the system also has done a work on the surrounding against its surrounding denoted by W. So the variation in the internal energy of the system can be written as a function of Q and as a function of the work W in the following way. So we can write down that U2 or U final minus U initial, which is given as delta U, it's defined as Q minus W. Okay, and this is what we call the first law of thermodynamics, where Q is the amount of heat added to the system and W is the work done by the system. And so this is called the first law. This is the first law of thermodynamics. Let's check that this relation it satisfies our definition. يعني خلينا نتأكد إنه إذا هون كان في عنا Q heat added to the system، هل الانرجي حتكبر أو حتصغر؟ وهل إذا كان هالسيستم عم يعمل work الانرجي حتكبر أو حتصغر يلي عنده؟ Let's check these two. So let's consider بأول نقطة to check إنه the system is not doing any work, so W is equal to 0, but that the system is gaining some heat. يعني Q is positive. الحالة شو بصير بالدلتا U؟ According to the equation, delta U هي بتكون positive. معناتها إنه U final is greater than U initial, which is quite correct and coherent. لأنه إذا كان السيستم عم يربح heat من ال surrounding، حكماً ال internal energy تبعيته حتكبر. So this first option is satisfied. Now, what happens if the system doesn't exchange any heat with the surrounding, but if he has done a work on the external surrounding? If W is positive, then we should expect that delta U is negative. ليش؟ لأنه إذا كان السيستم عم يعمل work, and according to our definition here, the work, positive work, means that the system is doing some work on the external surrounding. لازم هو يكون عم يخسر energy. نتأكد هل هيدا الشيء صحيح؟ So this is what we should expect. But is that correct? Yeah, because إذا بنحط Q equal لزيرو بيطلع معنا delta U equals minus W. بما انه W is positive يعني delta U is negative as we expect. So also in the case of the work doing some work on the external surrounding, the first law of thermodynamics is coherent with what happens with the system. Okay. So this is the first law of thermodynamics that we should memorize and you should know. Now, you may find in some references, instead of talking about delta U equals Q minus W, you may find that the first law of thermodynamics is stated and written as a function of the work done by an external agent on the system. يعني إذا كان بدل ما يكون في عنا W defined as the work done by the system, you may find W external defined as the work done on the system by an external agent. So in this case, إذا إحنا شفنا بالchapter 7 إنه we can write down W external as minus W. إذا كان الwork عم ينعمل على السيستم بتكون قيمته ناقص الwork يلي السيستم عم يعمله لبرا. And so بهالطريقة هيدا بنقدر نكتب ال first law of thermodynamics as delta U equals to Q. هي Q minus W, right? بس مع انه هون ال W can be written as so من هيدي الايكويشن فينا نكتب انه W هي minus W external. so اذا حطيناها بقيمتها بتصير equal ل so it's equal to Q minus هون بنحط ال W بقيمتها اللي هي minus W external. الماينس مع الماينس بيروحوا بصير في عنا Q plus W external. So إذا كان في عندكم W external as given, you can use this relation delta U equals to Q plus W external. But نحن ما حنعمل هيك خلال الاكسرسايزز والبروبلمز. What we are going to do هيدي بس مرقناها هون بالصف لحتى إذا شفتوها تفهموا شو هي وتعرفوا شو معناتها. Okay, بس نحن ما حنستخدم هيدي relation. We are going to use all the time only one version of the first law of thermodynamics اللي هي given by delta U equals Q minus W. Where Q is the heat added to the system and W is the work done by the system. إذا هو قالنا بالgiven إنه ال work is done on the system فإذا بنحط مباشرة W negative value. يعني إذا كان قالنا مثلا the work done on the system is equal to 10 joule, then we can write down W equals minus 10 لحتى نقول إنه this is the work done on the system. وساعتها بنستخدم بس هيدي الريليشن بشكل coherent ومن دون ما نوجع راسنا. Okay, now let's move on with an infinitesimal change of state. Let's assume that you have a system undergoing an infinitesimal change of state during which you have added an infinitesimal amount of heat, dq, let's call it dq, and during which the system does an infinitesimal work against its surrounding, which we are going to call or denote by dW. Then the first law of thermodynamics, it becomes, or it can be written as du, with infinitesimal variation in the internal energy in the of the system, it's equal to dq minus dW. And this is exactly the same as the first law of thermodynamics. هي نفسها عمليا، بس الفرق الوحيد انه هون ما عم نحكي عن given amount of change، but عم نحكي عن infinitesimal amount of change. Now make sure that, so also before to go on, this can be written as كمان إذا بنحط ال dW بقيمته ما ننسى إنه dW we have seen it earlier هي عبارة عن PdV. So we can write down then, if we replace dW with PdV, we end up also with another form of the first law of thermodynamics where we have du equals to dq minus PdV. So of course this is the same relation أنه بطبيعة الحال dW equals the PdV, but both are useful depending on where we are using them. Also note that هون الديو هي عم تقول لكم قد ايه عم بصير في variation بالinternal energy. So الinternal energy هي عباره عن energy مخزنه بقلب الجسم. وهالفاريشن بتقلنا قد ايه عم ينقص او عم بقل الinternal energy للسيستم. But you have to take care about something very important. هون dq is not the amount of heat contained in a body. dq هي it's about, or it can be defined or seen as the energy transfer as a result of the difference in the temperature between the system and the surrounding. يعني هيدي الدي كيو منا كمية هيت موجودة بقلب السيستم مخزنة والسيستم عم يخسرها أو عم يربحها، لا، هسه كمية الهيت هي عبارة عن energy interchange between the system and the surrounding بسبب فرق التمبريتشر بين هالتو entities، السيستم والsurrounding اللي لا. So these two relations, they are also useful, and we are going to use them extensively in the end of the chapter. So in this section, we will discuss heat capacity and specific heat. When energy is added to a system and there is no change in the kinetic or potential energy of the system, the temperature of the system usually rises. So if you're dealing with a system that consists of a sample of substance, and you want to find the quantity of energy required to raise the temperature of a given mass of this substance by a given amount, this varies from one substance to another. If you're dealing with water, that is different from copper, and it's different from other substances. So this is why we define what we call the heat capacity. So the heat capacity of a particular sample of a substance is defined as the amount of heat needed to raise the temperature of that substance by 1 degree Celsius. So this is why we define the heat capacity as capital C equal to 1 over N times dQ over dt, where dQ is the amount of heat needed to raise the temperature of this substance by the infinitesimal amount dt. And another quantity also of interest is the specific heat. The specific heat, which is denoted by small c of a given substance, is defined as the heat capacity per unit mass. So this is why we define by m in here. So C is equal to 1 over m times dq over dt, where again dq is the amount of heat needed to raise the temperature of the substance by dt. Now, actually, we have two specific heats that are important. Usually, when we heat or we cool some substance like a gas, for example, this can be done in several ways. So it could be done at constant volume, could be done at constant pressure, but also it could be done in such a way that P and V are allowed to change in some specific way. So here we are interested in two specific heats, which are the one defined at constant volume, which means when we add heat to a system such that we raise the temperature of that system, keeping a constant volume, and the second one keeping a constant pressure. So we are going to do this exercise. We're going to take the experience of raising the temperature of a given system by dt, by adding a given amount of heat dq at constant volume as well as at constant pressure. For this reason, we're going to consider the case of an ideal gas, because an ideal gas is the best and easiest substance to deal with. And so we will consider first, this is our ideal gas inside a container. And so we will supply an infinitesimal amount of heat to this substance. So we will introduce some dq in such a way that the temperature is raised by a given value dt. Okay, so we will put some dq in order to increase the temperature by dt. And all of this happens under constant volume. So which means that the container doesn't change its volume. So in this case, how can we write down CV, so heat capacity at specific, at constant volume, which is a specific condition? So let's consider the first law of thermodynamics. From the first law of thermodynamics, we can write down the internal energy of thermodynamics. We can write down that du, the infinitesimal variation of the internal energy of the system, is equal to the infinitesimal amount of heat added minus the infinitesimal amount of work done by the system. Since here we are dealing with a constant volume container, and we should not forget that dW is nothing else than P dV. But since dV is 0, because there is no variation in the volume, we are undergoing an experiment under constant volume. So that means that du is reduces to dq only. And we know what is dq, right? In this case, we know that the heat is supplied to the system and it is converted to internal energy. And all of this happens at constant volume. So we know that in this case, the heat capacity is defined as 1 over n, right, times dq over dt. And since this happens at constant volume, we will actually add a v, just the letter v, to say that it is happening at a constant volume. But since in this case dq is nothing else than du, because according to the first law of thermodynamics, since this process is undergone under constant volume, so dw is equal to 0, and so we can write down du over dt. And from here we can deduce, or we can conclude, that the change in the internal energy of an ideal gas when you undergo a process under a constant volume is given by N times CV times dt. So which means that the variation in the internal energy of an ideal gas is proportional to the variation in its temperature, and the variation in the temperature of this ideal gas. And of course, the coefficient of proportionality, it includes the heat capacity at constant volume, CV. Now, we can do the same experiment now, but instead of having a constant volume condition, we will have a constant pressure. So what happens in this case is that we're going to put our ideal gas inside a cylinder, and this cylinder is equipped with a movable piston. So the piston, it can move slowly to maintain a constant pressure all the time. And we are going to do exactly the same experiment. So we're going to supply this system by dq in such a way that the temperature of this system, which is initially given by T, would increase by an amount dt. And so we're going to do exactly as we did previously. So let's apply the first law of thermodynamics. Let me just write it down. So according to the first law of thermodynamics, we can write down so du is equal to dq plus dw. Oops, it's minus dw, sorry. So it's minus dw, dq minus dw. Okay, now let's have a look. What we want is that we want to define how much is Cp, right? And Cp is equal to 1 over n dq over dt, just like we did in the previous part. So we need to determine dq, okay? We can determine it from the first law of thermodynamics. Here we can conclude that dq is given by du plus dw. Now, how much is du and how much is dw? Let's have a look at that. So we know that dw is equal to pdv, right? Now, how much is equal to this pdv? Okay, we can do something actually. We know that from the ideal gas law, or from the ideal gas equation, that PV is equal to nRT, right? So we can differentiate this equation. يعني فينا نعمل differentiation لهالايكويشن بشكل انه differentiation D لل PV is equal to D لل nRT. هيدي الخطوة بالعادة بنعملها قبل ما نوصل على الديريفاتيف، اوكي؟ So كيف بنعمل differentiation لهالبارتس اذا كان في عندكم differentiation لاثنين مضروبين ببعضهم، so مثل كانكم عم تعملوا derivative. This gives اول وحده بتعطينا d للبي دي في بتعطينا دي بي مضروبه بالفي بلس بي مضروبه بالدي في. is equal to هلا هون بهيدا الترم بما انه ما في شيء variable غير بس التمبريتشر، فاذا هيدي الدي ما بتعمل اكشن غير بس على التمبريتشر، وبالتالي بنحصل على ان ار دي تي، لانه الان والار هن عباره عن كونستنتس وما بيتغيروا، وهيدي الدي هي عباره عن بتفرجينا قد ايه بيتغيروا الفاريبلز وكيف بيتغيروا بالنسبه لبعضهم. فطلع معنا هيدا الشيء. طيب بما انه هون احنا عم نشتغل under constant pressure، يعني there is no variation of the pressure, which means that this factor is simply zero, and so we only end up with PdV equals to nR dt, and so we can conclude that finally انه dW اللي شبناها قبل شوي اللي هي equal to PdV by definition, in this case it's given by n times R multiplied by dt. So we know what is dW. That sounds great. And also we know that du is equal to ncv times dt. So this we have seen it previously. هي شفناها بالبارت اللي قبل لما كنا عم نحكي عن under constant volume. And what you should know إنه this equation or this relation is valid whatever the process is that the ideal gas is undergoing. ايا كان البروسيس اللي الايديال جاز عم يعمله، هيدي الريليشن اللي هي variation of the internal energy of the ideal gas is always equal to n times cv times dt. So now we know what is du and we know what is dw. All what we need to do is to replace these two variables بالايكويشن اللي لهم هون بالايكويشن تبع هيدي الايكويشن dq equals ل du plus dw. So في عنا dq بنعرف شو هي، dw صرنا نعرف شو هي، وكمان du بنعرف شو هي. إذا بنجمع هول الثلاثة equations سوا شو بيطلع معنا؟ بنحط فإذا Cp it's defined as 1 over n dq over dt, right? So it is equal to 1 over n times dq هي عبارة قلنا du plus dw. So du هي ncv dt plus dw هي nr dt divided by dt, right? And so from here we end up with cv plus r. So from here we can conclude that the relation between Cp with Cv for an ideal gas is given by Cp minus Cv is equal to R. Okay, and that means that Cp is always greater than Cv. The heat capacity at constant pressure is always greater than the heat capacity at constant volume. يعني energy, the amount of energy that you need to increase the temperature of an ideal gas at constant pressure is more than what you need to increase the temperature of this ideal gas at constant volume. And the amount قد ايه الفرق بيناتهم هو عبارة عن ال R. So this we call Mayer's law. And we should know this, we should keep this in mind, okay? Another thing that is very important to define is to define the ratio of these two variables. So the ratio of the heat capacities at constant volume and at constant pressure for an ideal gas, as so this ratio is given by Cp over Cv. مع انه Cp is always greater than Cv معناتها انه هيدا الريشيو is always greater than 1. هلا نحن بنعرفه as given by gamma. رح نشوف بعدين بالسكشن يلي ورا هالسكشن انه we will use the ratio between Cp and Cv. لحتى ما نكتب كل مره Cp over Cv رح نعرفه as gamma factor، وهالجاما هو بنقول عنه الريشيو ما بين Cp وما بين Cv. In this part, the final part, we're going to discuss what are the possible thermodynamic processes and those which are of interest for us, let's say, those which we are going to study in our cases. So there are 4 types of processes that occur often in practical, which are, as you can see them here, 1, 2, 3, 4. So the first one is called isochoric, and isochoric means that it occurs at constant volume. The second one is called isobaric, and that means that it occurs at constant pressure. The third one is called adiabatic, and in the adiabatic process, we don't have any heat transfer, so there is no heat transfer at all between the system and its surrounding, which means that dq is equal to 0. The amount of heat transferred is 0. And finally, isothermal, which means that the process is happening at constant temperature. So temperature. Okay, now we are going to draw all these processes in what we call the PV diagram. So لما يكون في عندكم هذا الجراف, which is P, the pressure as a function of the volume, we call this a PV diagram. And I will show you that we can draw these processes on a given graph like that. So we are dealing all the time with ideal gases, and we know for an ideal gas that the relation between the pressure and the volume is given by PV equals to nRT. Okay, so this corresponds to a given curve like that. Okay, start again. So this corresponds to a given curve like that. And also it corresponds to different curves. That depends on the value of the temperature. So if we take different values of the temperature, that gives actually this kind of curves, which are close to each other in some places. And okay, so here it is. And so as long as you go high in temperature, you end up with more curves. So هيدي هي PV equals to nRT as drawn on this PV diagram. Now اللي بدنا نعمله هو رح نوقف على مكان ما بهيدا الجراف. Let's say I'll take this point, okay, on this point. I will sit on this point. I will take this to be my initial point, so I call it A, for example, هالنقطة. And then رح افترض انه بكل مكان حامشي فيه حامشي through 4 paths 1 2 3 and 4. okay, ورح نرسم كل process على ال PV diagram. So let's start with the first one. The first process that we call process number 1, it's called isochoric. Isochoric which means that we have a constant volume. يعني نحن عم نتحرك ما بين الكيرفز طلوع أو نزول بس عم نمشي على curve which does not change the volume of the يعني عمليا نحن عم نمشي على هيك نوع من الكيرفز. هيدي for example this is defined as an isochoric process, okay, and this path is called path number 1 to say that this experiment or this process occurs at constant volume. هلا ممكن الترانزيشن تكون على اول كيرف او الثاني او الثالثه، مش بالضروره مثل ما انا حطيتها هون النقطه بهالشكل، but the point is to say انه الفوليوم بهالترانزيشن حسب البروسيس 1 ما بيتغير ايا كان نقطه الانطلاق او ايا كانت نقطه الوصول. طيب بالنسبه لثاني بروسيس اللي هو رقم 2 it's called isobaric, it's at constant pressure. يعني نحن بنمشي من هالنقطه A لحيلا نقطه B بس ما بنتحرك نهائيا بالنسبه للبريشر، يعني البريشر بتضلها كل الوقت هي ذاتها بهيدا البروسيس. and so this path is called number 2. هيدا هو. في عنا رح بلش بالفور قبل ما نروح على 3. الفور it's an isothermal process which means at constant temperature. طيب شو يعني constant temperature؟ يعني there is no change, there is no variation in the temperature. معناتها انه احنا بنبقى على نفس الكيرف. اذا كان if we are undergoing, if our system is undergoing an isothermal process, that means that our system is moving on this curve بهالشكل هيدا. Okay, so this is the path for the let me just throw it away, the path of the process number 4. وباقي عنا الadiabatic process. هلا بالadiabatic process we will see that whenever you have an adiabatic process you will have a change or variation in the temperature of the system سواء كان بطلوع او بنزول. فلهالسبب هذا الشيء بيعني انه نحن رح ننتقل من كيرف على كيرف، لانه هون كل كيرف it corresponds to a given temperature. So whenever you are dealing with an adiabatic process, the temperature of the system of the ideal gas will change, and so you are moving always from one curve to another. Like in this case, for example, you may be moving to this curve, مثلا. Right, let me just do it again. So here it is, for example. And so this is the pass number 3. Okay, so هذا الشيء لازم نصير نعرف كيف نحن نرسمه. يعني لما تشوفوا على PV diagram these paths, you should be able to understand what does this path mean, واذا كان isochoric, isobaric. هلا usually ما بين الادياباتيك وما بين الايزوثيرمال عاده بيكون في فرق بسيط، انه الايزو ثيرمال بتكون الكيرف سموث اكثر، بينما الادياباتيك بتكون الكيرف شوي قويه اكثر نزلتها، يعني ببين انه هي عباره عن ترانزيشن ما بين two curves. Okay, let me just draw it again. Sorry for that. Like this. هون ببين انه هي نازله من كيرف على كيرف بشكل اقصى من مجرد ايزوثيرمال. الايزوثيرمال بتجي الكيرف سموث اكثر، وبالتالي السلوب اللي لها بتكون مختلفه. هون السلوب لل 3 البروسيس 3 اللي هو الادياباتيك بيجي شارب اكثر من السلوب للبروسيس نمبر 4 اللي هو الايزوثيرمال. So now what we are going to do is that we're going to investigate each process لحاله. اوكي رح نحاول رح نرسمه على رسمه. رح ناخذ كل process isochoric, isobaric, isothermal and adiabatic, and we're going in each case to write down what is du. Okay, so let's start first with the isochoric process. An isochoric process, it occurs at constant volume, which means that you have, if you go from this initial state and you go down to this final state, this occurs on a straight line without any change in the volume of the system. And so how the variation of the internal energy is written in this case. So in this case, we are dealing with, so let's write down. The first law of thermodynamics tells us that du is equal to dq minus dw. And again, we can write down dw as given by p dv. But since here we are dealing with an isochoric process, which means that there is no variation in the volume, that parameter goes to 0. And so in this case, du is only equal to dq. So that means that all the energy added as a heat into the system will remain in the system as an internal energy. يعني هون السيستم بهالحالة عقد ما أخذ هيت من برا حيحتفظ بهيدا الهيت as internal energy، وبالتالي مخزون الانترنال energy عنده حيكبر إذا كان عم ياخذ هيت من برا. Okay, so we can reduce that for an isochoric process. du is equal to dq. Okay. Now let's move on with an isobaric process now. For an isobaric process, so in this case, again, if you have two points like this, if we are moving from this point, اللي هي initial state. Okay, so if this is our initial state, then فينا نمشي باتجاه اليمين أو باتجاه الشمال. اثنيناتهم they are okay. It depends if you are making an expansion or if you are making a compression. بس الفكرة إنه we always have to move on a straight line. ما بنقدر نمشي لفوق أو لتحت. ليش؟ لأنه البريشر لازم تضلها constant, which means that هيدا اللاين ما بيقدر يطلع لفوق أو لتحت. Okay. So in this case, how we can write down or how we can express du? So again, according to the first law of thermodynamics, du is equal to dq minus dw. And since dw is equal to pdv, then we can write down du as equal to dq minus pdv. Now, of course, if p is since p is constant, then دغري فينا نقول انه الدلتا يو هي كيو ماينس بي دلتا في. يعني هون ما ننسى انه البي از كونستنت، وبالتالي only الفاريشن هي ب دي في، فالانتجرال بس بصير على دي في حصرا. Okay, and so this is the equation in this case. It's given by dq minus p dv. Now we are going to deal with an adiabatic process. So adiabatic process is defined as the one with no heat transfer occurs into or out of the system. So there is no heat transfer at all between the system and its surrounding. And actually we can do this kind of process, what we call the adiabatic, either by surrounding the system with a thermally isolating material such that the heat cannot flow into or out of the system, or by carrying out the process so quickly that there is no enough time for heat flow. يعني نعمل البروسيس بشكل كتير سريع such that ما في الهيت تطلع او تفوت من السيستم. اوكي هلا هون السؤال هو في 3 actually relations من خلالهم بنقدر نعمل relation ما بين ال variables P, V and T اللي هن ال pressure, the volume and the temperature. Because as you might have guessed already, the adiabatic process, it doesn't correspond to a constant volume or a constant pressure or a constant temperature. So all these 3 variables, they may change in this kind of process, but there is a way, there are some equations which dominate أو بتقلنا كيف بيتغيروا. هالrelations هن كالشكل التالي: P V to the power gamma equals to a constant. هي أول relation اللي بتقلنا كيف ال P وال V بيتغيروا بالنسبة لبعضهم. Another relation which is T times V to the power gamma minus 1 equals to a constant. كمان هالrelation بتخبرنا كيف ال temperature مع ال volume بيتغيروا بالنسبة لبعضهم. And the last one is given by T to the power minus gamma P to the power gamma minus 1 equals to a constant. كمان هيدي بتعطينا آخر وحدة relation ما بين ال temperature وما بين ال pressure. So in this section we are going to see and to derive all these equations, all these relations. رح نجيبهم سوا ورح نشوف كيف بنوصل لل PV gamma equals to a constant for example. We will do it only for 2 اللي هن أكثر شيء familiar وأكثر شيء رح نستعملهم، والباقي بس رح نحطها لحتى نخليها to memorize it. Okay. So in a adiabatic process, if you want to write down the expression for the variation of the internal energy according to the first law of thermodynamics, we can write down du equals to dq minus dw. But in this case, since there is no heat transfer at all, that this factor is just equal to 0, then du reduces to minus dw. Okay? Now, let's derive these equations, which we have seen previously, that relates all the 3 variables together: the pressure, the volume, and the temperature. And for this reason, let's consider an infinitesimal change of the state of the ideal gas given by dp, dv, and dt. Okay? So we're going to write down all the relations اللي بيعطونا كيف ال V بتتغير وال P بتتغير والtemperature بيتغيروا بالنسبة لبعضهم. And from out of these equations, we're going to find relations between P and V لحال, P and T لحال, و V and T لحال. So first of all, we can write down, according to the first law of thermodynamics, that du is equal to minus dw, يعني is equal to minus P dv, right? We also know that for an ideal gas, the variation of the internal energy is equal to the variation of the temperature through the 2 factors NCV, so NCV dt, okay? If you combine these 2 equations, then you end up with NCV dt is equal to PdV. وهيدي الريليشن اللي طلعت معنا هلا تجمع ما بين ال variation of the temperature وال variation of the volume. So let's call this equation, or let's just put this equation in the box حتى نحتفظ فيها. هنرجع بنسميهم بعد شوي. Okay. Also, we shouldn't forget the equation for the ideal gas law, which is given by PV equals nRT. And we're going to do as we did previously. So we're going to differentiate هذه equation. يعني we want to apply the operator D اللي هو differential على هالايكويشن بشكل انه نشوف كيف هالفاريبلز بيتغيروا بالنسبه لبعضهم. And so this gives us dp times v plus p times dv is equal to nr dt. Okay? Oh, here we have a minus sign. Just forgot a minus sign. Is equal to minus p dv. Okay? And so this is another question. Okay? Now let's call this number 1. And let's call this number 2. Okay, so it's not writing. We call it number 1. And this we're going to call it number 2. So now if we sum up equations 1 and 2, so we just do 1 plus 2, we will end up with يصير في عنا minus p dv plus p dv بيروحوا بعضهم بيبقى عنا v dp is equal to n cv dt plus n r dt. إذا بنحط ال n in common factor مع ال dt بيطلع معنا n cv plus r dt. With cv plus r, as we have just seen previously, هي nothing else than cp. So from this we can deduce a new equation given by vdp equals to ncp dt. واجين مثل ما نكون شايفين هالايكويشن بتجمع ما بين الفاريبلز p والt لانه بس بكون شوفوا اي فاريبلز هن they are considered بيطلعوا على شو في بالديفرنشال. هون في دي بي ودي تي، يعني هالايكويشن بتساعدنا نلاقي ريليشن ما بين البي والتي. هون في عندنا ايكويشن ما بين دي تي والدي في، دي تي والدي في، معناتها كمان في ريليشن هون ما بين الفي والتمبرتشر and etc etc. So now we will start with the first one. احنا بدنا نجيب هلا relation ما بين البريشر وما بين الفوليوم. So لهالسبب بحاجه انه نلغي temperature. We have to eliminate the temperature. Okay. Let me just call this equation number 3 حتى يكون عندنا كل شيء واضح. Okay. So this is the equation number 3. Now let's go on. So بدنا نلغي لنا temperature. طيب have a look. إذا بنقسم equation 3 على equation 1, we can actually get rid of the term about including temperature. ليش؟ لأنه شو بيطلع معنا 3 over 1 بيطلع معنا V dP divided by minus P dV is equal to NCP dt divided by NCV dt. Right? And don't forget that dt and dt and نفس الفاكتور والn هو نفس الفاكتور اللي بيعطينا بالأخير إنه هيدا it's nothing else than Cp over Cv. And if you still remember, this is nothing else than the gamma factor that we have defined previously. Okay, so من هون صار في عنا variables differential in pressure و differential in volume. لازم نجمع البريشر لحال والفوليوم لحال. هذا الشيء بيعطينا هون هيدا بحط البريشر مع البريشر بنخليها بيطلع معنا dp over p. Let's keep it with a minus sign. Okay, is equal to gamma dv over v. And so that gives us dp over p plus gamma dv over v is equal to 0. Now, if you make an integral for these two factors, بيطلع معكم integral of dp over p plus integral of gamma dv over v. And so this can be written as ln p plus gamma ln v. This is constant. لأنه الانتجرال لل dx over x هي عبارة عن اللن. وهون الزيرو بيعطينا بالاخير constant. So we can put الجاما بقلب الاكسبريشن للن بتصير هي so بتصير ln p plus ln v to the power gamma is equal to a constant. ونحن بنعرف انه ln لتو variables summed up هي عبارة عن البرودكت لهم اثنيناتهم. So ln p v to the power gamma is equal to a constant. And so from here, we can deduce that the product PV to the power gamma, P times V to the power gamma is equal to a constant. So لما نقول equal to a constant يعني بنعني if you look at the state of the ideal gas at two different time during the process, you will end up with PV gamma equal to a constant. So this is the way the pressure and the volume change with respect to each other. Okay, so this is it for the first equation, for the first relation. Now we are going to move to another relation. We are going to show اللي هي ما بين temperature وما بين الvolume. So now how the temperature changes with respect to the volume. Let's have a look back at the equations. طيب, if we take the equation number 1 already. So the equation number 1 شو بتعطينا؟ The equation 1 بتقلنا انه في عنا minus PdV. Let me write it down. Minus PdV equals NCV dt, right? Let's replace P by its value. يعني احنا بنعرف من ideal gas انه P V equals nRT. So we can replace P by nRT over V. بهالشكل بنكون تخلصنا من البريشر وبقي عندنا بس الفاريبلز اللي هن الفوليوم اللي هن temperature. So we end up with minus nRT over V dV is equal to NCV dt. Okay. We can get rid of the factor n on both sides. And let's keep in here dv over v. Okay. وهون في عنا r مضروبة فيها. رح ياخدها لتاني جهة بتصير plus cv dt over t is equal to 0. Okay. Now we can actually divide r by cv. فبيطلع معنا هون r over cv dv over v. يعني بنخلي هذا الفاكتور يكون بس باحد البارامترز مش موجود باثنين. So dv over v plus dt over t that is equal to 0. هلا بس على جنب ال r over cv هي عمليا ال r هي cp minus cv. اوكي كلها divided by cv فهي عبارة عن gamma minus 1. So we end up with gamma minus 1 dv over v plus dt over t that is equal to 0. نجي بنعمل integral لهالايكويشن بيطلع معنا len. So gamma minus 1 len v plus len t equal to a constant. And so this yields finally the relation TV gamma minus 1 equals to a constant, which is the relation between the temperature and the volume in the case of an adiabatic process undergone by an ideal gas. And so finally, we can show that in the same way, so using these equations 1, 2, and 3, we can show that the relation between the temperature and the pressure is given by T to the power minus gamma, P to the power gamma minus 1 is equal to a constant. T to the power minus gamma and gamma minus 1. And so this is the third equation, which actually describes the relation and how the temperature and the pressure, they vary with respect to each other in the case of an adiabatic process. Now, one more part or subsection which is important, which is the work done. We are going to do together the work done by an ideal gas, okay, during an adiabatic process. And actually, once we do this part, you can use the result in any question, in any problem, without having to derive it again. Okay. So in the case of an adiabatic process مثل ما شفنا إنه ال dq is equal to 0. That means that the internal energy du, it reduces to minus dw. And since dw, or since du is equal to ncv dt, from here we can write down immediately that dw is equal to minus du. So it's equal to minus ncv dt. And so if you just do the integral on both sides, you end up with the integral of this one is equal to the integral of this one. And so you end up with the work done by an ideal gas during an adiabatic process. It's given by minus n times Cv integral of dt between, let's say, T1 and T2. Okay, and so this is given by minus n Cv T2 minus T1. And so this expression for the work, you can use it immediately without having to derive it whenever you need it. Okay, but this expression is, this expression, it gives or it describes the work in terms of the temperature T1 and T2. هلا ممكن انتم بحاله ما كان عندكم التمبريتشر كان في عندكم البريشر والفوليوم كمان still you can deduce this expression, or we can still see how much is the work. So بما انه الورك طلع معنا هو عباره عن minus ncv T2 minus T1, right? ونحن شفنا من ideal gas انه PV equals to nRT. So we can replace T by P times V over, okay, P times V over N times R. So إذا بنحط هذا الشيء بقيمته بيطلع معنا minus NCV P2 V2 minus P1 V1 divided by N times R. Okay, and so now we can cancel out both the N and N. كمان ال R over CV بنعرف شو هي gamma minus 1. So we end up with W given by minus P2 V2 minus P1 V1 divided by R over CV. Well, R over CV هي gamma minus 1. مع ال minus 1 بتصير so P2 minus P2 V2 minus P1 V1 divided by gamma minus 1. Gamma minus 1 مع ال minus sign بتصير 1 minus gamma. And so we can write down the work as P2 V2 minus P1 V1 divided by 1 minus gamma. And this is it. So we can write down فإذا the work as minus NCV T2 minus T1 إذا كان عندنا temperature، وإذا ما كان عندنا temperature فينا دغري مباشرة نجيبه من خلال the pressure will volume if we have the pressure and the volume using this second relation. So in this section, we're going to study the relation between the volume and the temperature for an ideal gas in the case of an adiabatic process. You remember when first we talked about the thermodynamic processes and we have drawn them on a PV diagram on this figure. We said that always an adiabatic process, which corresponds to number 3, so the red curve, we have a change in temperature. Either temperature increases or decreases. And for this reason, this is what we are going to study to see how the temperature changes during a volume change in the case of an adiabatic process. And this is why we're going to use the equation that we know now that relates temperature to the volume, which is given by T times V to the power gamma minus 1 equals to a constant. So here's the PV diagram. And let's suppose that we are sitting on a given point, which we call point 1, which corresponds to a well-defined state of the of this ideal gas. So it corresponds to P1 and a given value of the volume, which is equal to V1. And of course, because it corresponds to one isothermal curve, so it corresponds to the temperature T1, okay? So now we're going to make an experiment during which the ideal gas will undergo an adiabatic transformation process. And so we're going to have a transformation from the initial state, okay, which is defined in terms of temperature and volume by T1 V1, okay, to some final state, which is defined by the temperature T2 and the volume V2, okay? Now, how these variables, they are related, we know from the equation T times V to the power gamma minus 1 that this is a constant. That means that T1 V1 to the power gamma minus 1 is equal to T2 times V2 to the power gamma minus 1. This is what means that the product T times V gamma to the power minus 1 is equal to a constant, okay? Now let's consider two cases. An expansion during which the volume increases, and the other case, which is a compression during which the volume decreases. So let's start first with the case of an expansion. And let's study what happens with the temperature if the volume increases. So V2 is greater than V1, obviously, and we can also deduce that if the ratio between V1 and V2, so V2 over V1 is just greater than 1. To say that this ratio is greater than 1, okay? Now, how T1 and T2, they are related? Okay, they are related in the following way. T1 over T2, if you just divide T1 by T2, that is proportional and equal to V2 to the power gamma minus 1 divided by V1 to the power gamma minus 1. So both have the same index, so it's or same power. So we can write it down as V2 over V1 to the power gamma minus 1, right? But since the ratio V2 over V1 is greater than 1, and since this power اللي هي gamma minus 1 is positive, لأن gamma is all the time greater than 1. Don't forget that gamma is defined as the ratio between Cp and Cv, and Cp is all the time greater than Cv, which means that this gamma factor is all the time greater than 1. That means gamma minus 1 is always positive. فإذا كان عندكم ratio already greater than 1 وعنده power positive, this means that this is always greater than 1. And that allows us to say that T1 is smaller than, T1 is larger than T2, which means that in this case, the temperature T decreases during during an adiabatic expansion of an ideal gas. Okay, so we can say that an adiabatic expansion of an ideal gas always occurs with a drop in the temperature. Now, let's see the case of a compression. For a case of a compression, we expect the opposite, but we will check this together. So in a compression, the volume decreases, so V2 is smaller than V1, and that means that V2 over V1 is smaller than 1. So again, since T1 over T2 is again equal to V2 over V1 to the power gamma minus 1, and since this ratio is smaller than 1 and the power is positive, that means that it remains smaller than 1, and so T1 is smaller than T2 in this case, which means that the temperature T in this case increases. And therefore we say that an adiabatic compression always occurs with a rise in the temperature. Now, how we can draw this on a figure, we are just going to do this, but let's write down first that an adiabatic expansion of an ideal gas always occur with a drop in the temperature of the gas, while an adiabatic compression always, of course, of an ideal gas, always occur with a rise in the temperature. And from here we can understand how to draw a curve for an adiabatic expansion or compression of an ideal gas on this curve. So let's do this together. Let's consider the case of an expansion. So for an expansion, we said that so first of all, in a case of an expansion, you should be moving from point 1 rightward لأنه عم يكبر الفوليوم، يعني عم نمشي باتجاه اليمين. And what happens with the temperature? Here we see that temperature decreases. يعني الانتقال حيصير من نقطة 1 على نقطة on a curve that is below this curve، لأنه هون التمبريتشر كل ما عليت كل ما بنمشي على curve أعلى منه. So بما إنه التمبريتشر عم تقل، يعني عملياً نحن عم نمشي من البوينت 1 ننزل على curve تانية تحت منها، لأنه التمبريتشر بتكون أصغر temperature على الكيرف من تحت. And so in this case, let's say this is the point 2 اللي هو ال final state, and this point would be characterized by the pressure and the volume P2 and B2, while the temperature has decreased. إذا كان الحكي بالعكس، يعني إذا كنا واقفين على a given point وعم نعمل compression، ساعتها بصير بالمقلوب. And in order to do this ما رح احط اي شيء على الدياجرام جديد، وانما اعتبروا حالنا انه الانيشال ستيت هو البي 2 نقطه 2، نحن واقفين على النقطه 2. اذا بدنا نعمل compression نحن ما نمشي باتجاه شمال، لانه بيكون الفوليوم V2 لازم يصغر ويتحول لفوليوم اصغر، فعمليا نحن حنكون عم نطلع طلوع على كيرف لفوقها، وبالتالي عم نطلع من البوينت 2 على الكيرف الخضراء على البوينت 1. سو شايفين بهالطريقه عم ننتقل على كيرف اعلى، وبالتالي التمبريتشر عم بتزيد مثل ما المفروض يكون حسب ما هون عندنا شفنا بالكمبريشن انه T increases, and so this is what happens. So this is why هون بالadiabatic process لما بدنا نرسم الكيرف in a PV diagram, there is always transition between one curve to another, لانه there is always a drop or a rise in the temperature of the ideal gas. So this is it for the adiabatic process. We just have one more process to not to study but just to summarize, which is an isothermal process. So finally, the isothermal process, as we said earlier, an isothermal process is characterized by a constant temperature. So it occurs at constant temperature. So in this case, actually, in the general case, none of the internal energy delta U or Q or W is 0 for an isothermal process. So in the general case, delta U, Q and W are different than 0. وهذا الشيء بنعني فيه انه نحن شفنا انه مثلا بالadiabatic process there is no heat, which means that Q is equal to 0. In the case of isochoric process, at constant volume, W is equal to 0 because W is equal to P dV. So in the case of isothermal, ما في particularly any of these variable which is equal to 0. But in the case of an ideal gas, بما انه الايديال gas نحن بنعرف انه الدلتا يو هي equal للNCV dt. So du is equal to NCV dt. بما انه dt is equal to 0, then this becomes equal to 0. So according to the first law of thermodynamics, we know that du is equal to dq minus dw. فبالتالي بتصير dq minus dw equal لزيرو بحكم انه du equal لزيرو for an ideal gas, and so in this case dq would be equal to dw, and this is it. So this is what happens in the case of an isothermal process undergone by an ideal gas. And so this is it for this chapter.